I've been flopping around in my notation, so let's be clear on notation. I was calling this f of t. I'm just going to call it r of t, capital R of t, vector r of t. And this vector r of t comes out to a point on a curve, and at that point we have the radial unit vector u sub r and the unit vector perpendicular in a right-handed sense to u sub r. We call that u sub theta. And we see that if r changes, if the length of the vector changes, the magnitude, that's going to be a change in the direction of ur, if the vector gets longer or shorter. And if the vector changes direction, it's going to cause a change in the direction of u sub theta. Now, I've also, you might have seen this earlier, I had arrows over these r's here, and these don't have arrows, so I've kind of used little pieces of paper to block those. So you might have seen this already with a different notation, and I've still got an f here that I'm going to change to an r. Okay. Now, we've seen that the derivative of ur with respect to t, after doing the derivatives, is equal to u sub theta times d theta dt, and also that du sub theta dt is negative u sub r times d theta dt. And we can make sense out of that in terms of these directions, but right now let's just use these ideas and repeat those here. Now, our r of t vector can be expressed in terms of right-handed coordinate system, xy coordinate system, as x of ti plus y of tj. Alternatively, we could write r of t as, okay, the vector r of t as a scalar function r of t. This is just a number. It's no longer a vector. Remember, I accidentally put arrows over these, eliminating those. So we have a function r of t times u sub r. That is, the r of t function is the magnitude of this vector. When I multiply the magnitude of the r of t vector by u sub r, I get a vector in the direction of u sub r with magnitude r of t. But since r of t is already in the direction of u sub r, then multiplying the r of t function, the scalar function, by u sub r just gives us the vector function. So, for very straightforward reason, our r of t vector is the scalar function r of t multiplied by our u sub r vector, and that's just our r of t times I cosine theta plus j sine theta. Now, if we want to take the derivative of the r vector with respect to t, of course we can do that in our rectangular coordinate system. We're just going to get x prime of ti plus y prime of tj. If we want to take the derivative of the polar form of this, the form with respect to the changing u sub r and u sub theta vectors, well, we take the derivative of r of t u sub r. Now, since vector r of t is scalar r of t times I cosine theta plus j sine theta, then our dr dt is just the derivative with respect to t of the I component, which is r of t cosine theta, plus the j component, which is r of t sine theta. And that comes out, well, derivative of the I component is, by the product rule, going to be r prime of t times cosine theta plus r of t times negative sine theta d theta dt times I, and then we have plus a very similar expression, r prime of t sine theta plus r of t times cosine theta d theta dt times j. If we collect these terms, we find that we have r prime of t times what? Times cosine theta plus cosine theta I plus sine theta times j. And that's just our r prime of t times our u sub r vector. And then it's plus r of t multiplied by negative sine theta I plus cosine theta j multiplied by d theta dt. And this vector is just our u sub r vector, and this vector here is our u sub theta vector. So we have this, our r of t, derivative of our r of t vector with respect to t is r prime of t times the ur vector plus r of t d theta dt times the u theta vector.